Okay, YouTube, this is my first video in my module on factoring, in which we're going to basically be doing the opposite operation of multiplication or distribution here. So what we want to do is consider the fact that if we were to distribute, say for instance here, this 5x through this binomial 2x plus 3, we would get this new expression 10x squared plus 15. The idea will be able to just like use what we know about multiplication of polynomials here to work backwards in order to say, well, maybe I noticed that both of these expressions have 5 in common in terms of their coefficients as a factor, a common factor, and maybe, I noticed that both of these have an x to the first that they could give. So if I were to not multiply out, but do the inverse of multiply, which is divide out that 5x, what would be left on the inside? And we noticed that we could re-obtain the initial expression here. So the goal of this video will be to break down polynomial expressions that are sums. So rewrite, this is our goal. Rewrite sums and differences as products of factors. That's what we want to do. And if you've done a factor tree before, you could look at it this way. We say 5x times 2x plus 3. That's essentially what we're doing, is making a factor tree and breaking things down if we can. So in terms of factoring, this first video is basically going to confront two really basic factoring methods that both involve common factors, which is what we basically just did up here. We found a common factor between every term in the sum and said, let's factor that out and rewrite this as the product of two polynomials. So let's take a look at this one here. We say in any factoring problem, the very first step, I say this, okay, is to look for the GCF, the greatest common factor. You should always look for this first, okay? So the greatest common factor, we abbreviate that, I guess, GCF, I wrote that here. It says, is an expression of the highest degree that divides each term of the polynomial. So it's basically the backwards of the distributive property. So if distribution is multiplication, the reverse is going to be division. We're going to divide out a common factor. And you know what, not just lose it, but we're going to keep it up front, okay? So for instance here, both of these terms have a common factor of a. We'll go ahead and say we'll factor the a out in front, and we notice that we could be right and check ourselves here by redistributing and seeing that we get back the initial quantity that we started with here. So let's go ahead and take a look at these two examples that I've got listed. Letter A, it says, okay, well I've got this binomial, third degree polynomial, and I want to know, well, can we factor out a greatest common factor? Well, in terms of their leading, or not the leading coefficient, but the coefficients themselves, I noticed that 10 and 4 are both even. So I could factor 2 out of both of those, and I notice also that x cubed and x squared, we could take 2 x's out of both of those terms, okay? So when I do this, it's important to note that what we're doing is the inverse or the reverse of distribution, which was multiplication. So what's left in here really gets divided by whatever we put out front. And in this case, we'd say, well, 10 divided by 2, that's going to give us a 5 here for a coefficient. And x to the third divided by x squared using the rules of exponents. Remember, x to the third over x squared is really x to the 3 minus 2, which is x. In other words, we just have 1x left if I took 2 of them out. Okay, so I have 5x here on the inside. We have a negative 2 divided by a positive 4 there is a negative 2. And we'd say, well, I lost both x's. Now, one thing I would point out is you could technically write I have 0 x's left because anything to the 0 power is 1. But we tend to just write it this way. And lastly, you can check your work by just remultiplying this and seeing if you get back what you started with. Now, letter B tends to throw people here. As a matter of fact, I already have some factored expressions within this sum. This is a sum of two terms. And just like in this last one here, or up here we say, what do these two terms have in common? I notice they both have a factor x minus 7. So it's going to feel kind of awkward at first, but we can take out this entire binomial out front. I'm going to say, well, I'm going to factor out their GCF, which is x minus 7. And when I write what's left, remember we're dividing out what we took out. So I took out both of those x's, x minus 7's terms there. And what I'm left with is really just the 2x and the positive 3 here. So I say 2x plus 3, and that's what's going to be left there. So multiplying this back out, you see you get the same thing you started with. Now, on this note, we're going to look at a very, very special factoring pattern here. We call this factoring by grouping. And it's written here, we say, some polynomials have only a greatest common factor of 1, okay? However, by a suitable grouping of the terms, it's still possible to factor sometimes. We call this factoring by grouping because we're going to group terms here. So as we illustrate here in this example number 2, basically what I want you to see is both of these expressions are four-nomials, okay? Factoring by grouping is typically used when you have a four-nomial. Not always, but typically, okay? And so I noticed that also none of these terms have anything in common. Their greatest common factor is really just 1. So what I'm going to do is I'm going to group together the first two terms. This is how this process works. Step 1 is we're going to group together the terms here. And I'm actually going to write that positive 3 right here. I'm going to keep it with my 3, not that it matters much in this instance. But we say, now looking at what we have, the second step will really be to say, are there any GCFs here, greatest common factors? And as a matter of fact, I see that they both have, two x's that they could give. So I'm going to factor that x squared out front. I'm going to say, well, what would be left? Well, I'd have 1x here, where there were 3 x's. And I say, well, this 4 right here is just going to be a 4 because I took both those x's out front. So this really essentially is what we've done is we've factored just the GCF out of the first two terms there. And I'm going to bring down this positive. And I'm going to say, okay, well, what do these have in common, GCF-wise now? And I notice that both of them have 3 as a factor. So I'm going to list that 3 out front. I'm going to put that in pink here. And we'd say, well, what's left is going to be x, and 12 divided by 3 is 4. And so the interesting thing about this is a lot like that last example we just looked at, where I said, well, I still have a sum of 2 terms. But what do they have in common? Well, they both have an x plus 4. So if grouping works, this is only true if grouping is going to work if it's factorable, then what's left inside these two quantities here is going to be something that they have in common. So this really is a GCF method, and what I'm going to do is I'm going to factor out the x plus 4 out front. I'm going to say, well, let's take that x plus 4 out front and write what's left, and since I divided that out of both of those, I'd say, well, x squared plus 3 would be left. And again, we could FOIL this back out to see that we get back to what we started with, okay? So it's worth our time to look at this one really quickly here. The reason why is because when we group these here, I'm going to say, well, I think grouping, because I don't see a GCF, but I think grouping also because it has 4 terms. Now you'll notice something here, I hope. I put a plus between these two parenthetical quantities, and I put that negative in front of the 2. You need to keep the negative in front of the 2. But really all we did was we just grouped these terms here, just like this, and I put a positive there. That's all I did. So again, GCF-wise, we'd say, well, they both have an x squared. Let's take that out front. In this case, I'd say x plus 5 is left over. Plus, now, what do these two have in common? Now, since they're both negative, or at least this thing here is negative, and really what I'm trying to have left behind is an x plus 5 so that I can factor those both out front, I'm going to factor out a negative 2. And that does leave me with, well, negative 2 divided by negative 2 is 1, x, and negative 10 divided by negative 2 is a positive 5. So this does also work by grouping. We're going to factor the x plus 5 out front with this grouping method. I get left with x squared minus 2, and this would be our factored expression.